All right, I think we can get going. Welcome back, folks. So before we get going with a lecture, just some quick announcements. As many of you probably heard, there was a shelter-in-place order on campus today, and since it was for several hours, and buildings are all closed, and as you probably know, all in-person lectures on campus are canceled for today. Pretty big disruption, and then on the day of our exam. So we paused the exam. You should all have received an email about this, but I know we don't often communicate through that channel. So if you haven't seen it already, please look for details there. We paused the exam, and then after the stay at home, or rather shelter in place order was lifted, we've sent an email about instructions on resuming the exam. Some high level bits are we've extended the submission deadline till tomorrow, Friday, at the end of the day, so 24 hours longer than we initially planned for. And some folks were disrupted while they were taking the exam when the shelter in place started. So there's some special instructions for those folks. Okay, but if you already submitted the exam, you're perfectly fine. If you haven't already started, then basically you have another 24 hours to do it. And if you were disrupted, then there's some special instructions for you in email. Okay. All right. So that's the announcements for today. Yeah, let me share my screen. Okay. So here's an overview of VR topics that I showed at the beginning of lecture yesterday, or on Tuesday rather. And we finished up on Tuesday talking about the first topic, VR displays. Lots of stuff to talk about in there that we covered in detail: head tracking, binocular stereo, how does it work, in the human visual system, how do we implement it, what are the details of implementing that in the displays and rendering, amongst other things. The continuation today goes into, aside from the headset engineering or the headset design and engineering and how those flow from characteristics of the human visual system, we're going to talk about rendering challenges in VR, rendering to these kinds of headsets, and then a sort of related topic with a whole bunch of other interesting technical issues: VR imaging. How do we build cameras that could capture the kind of information for us to show in these kind of headsets with the same kind of three-dimensionality, immersion, 6 degree of freedom, parallax as we enjoy in VR displays today. Lots of challenges there. Okay. All right, so let's get going with rendering. One of the big things that comes up in rendering for VR, the first big one really, is that there's a really strong requirement for low latency in order to provide the key perceptual experience of virtual reality. So that's hard because the resolution requirements are also high. So as a reminder, last time I put up this slide and we talked about how to you get a retina display that sort of reaches the limits of acuity of the human visual system. So something like 60 pixels per degree is what reaches the human acuity limit. And if we were trying to do that for a VR headset, something on the order of like 128 megapixels might need to be rendered for the two eyes in such a VR headset, at least according to current designs. And I'll get into the sort of foveated rendering issues in a second. But first, the latency requirements. They're very challenging in VR. And the reason for that is the goal of the VR graphic system is to achieve a sense of quote unquote presence for the user in that headset. And that means tricking the brain into thinking that what it's seeing is really like some 3D world that exists out there. And achieving that kind of presence requires an exceptionally low latency system, because what you see must change when you move your head at a fast enough rate that the brain is fooled right into thinking that it comes from the real world. So what are those kind of end-to-end latency requirements? Well, the way to think about it, it's that the time from which you move your head to the time at which new photons, which get emitted by pixels inside the display, the time when those new photons are emitted and then will strike your retina, that's the end-to-end latency time. And that needs to be short enough to approximate as if the light came from a physical world that was three-dimensional that we're simulating. So what goes into that end-to-end latency time? We need to measure the user's head movement, right? That has to do with all that head tracking stuff that we talked about last time. So all of the measurement, physical measurement of the data for that, and then the processing. Sometimes there was video processing that we talked about last time. There might be communication time to get the information if it was from an external camera and an external computer through to the headset, for example. All of that is in measuring the user's head motion. We then need to update the scene and camera position. We need to render a new image that will take GPU processing time. If the GPU was in an external computer, we would need to transfer that image to the headset. Of course, a lot of headsets these days actually have the GPU on the headset itself. In any case, we then need to transfer that information from GPU memory, for example, through to the display itself. And then the display itself needs to actually physically emit the light from the display surface. And since speed of light is very fast, as soon as it's emitted, pretty much the photons that are emitted will hit the user's eye, so that speed of light time doesn't really contribute to the latency in an appreciable way. But the rest of this stuff does, and it has to really do with measuring, computing data, and communication. So all the computer engineering stuff. The final latency goal of VR is something like 10 to 25 milliseconds end to end for all of that stuff that I just described. So that requires exceptionally low latency head tracking, and it requires exceptionally low latency rendering and display hardware. So here's a thought experiment on why it needs to be so low, what the effect of latency is in this kind of a system. So let's consider a 2000 by 2000 pixel display that spans 100-degree field of view. Okay, this doesn't match any specific product that's on the market today, but as I described some of the products last time, it sort of sits in between some pretty common products in that you could buy today. That would end up being about 20 pixels per degree. Okay, visual angle again. Now assume that you move your head 90 degrees in about 1 second. So that would be like, I'm looking at you, 1, 1000, 2, 1000, 3, 1000. It's like that sort of a turn. Okay. So 90 degrees in 1 second, which, by the way, you can tell is pretty modest speed. You might move your head much more quickly than that in VR very commonly. So this is a sort of pretty moderate test. The end-to-end latency of this system, let's assume, though, that it's kind of a low latency system, a latency system that's not very well optimized yet. Let's assume it's 33 milliseconds, which would be as if like 1 frame per second at 30 frames per second. Like, let's say all the processing happens within 1 frame at 30 FPS. That's nowhere near good enough, it turns out, to generate presence in a visual manner that's going to be convincing in VR, because the displayed pixels in this situation would end up being off. You can calculate this 33 milliseconds at 90 degrees per 1 second velocity with 20 pixels per degree. And you can calculate that it'll be 3 degrees off. The display pixels would be 3 degrees off because of that latency, which would end up being 60 pixels, okay, a lot of pixels off from where they should be in an ideal system with 0 latency. This kind of error, it turns out, will lead to, as the person moves their head around, like a lag in the visual appearance of the world relative to their head motion that they're feeling with their vestibular system. And it will be very visually disorienting. And for extreme latencies of this the kind of thing that make people feel really ill or puke in VR, okay? So getting VR latency super low for rendering is required in order to avoid these kinds of, these kind of lags and the kind of perceptual and sort of nausea-related effects that are a common problem. One of the big rendering challenges, again, let's dig into this more, is that low latency and high resolution require really high rendering speed. And you might imagine that engineering challenges to try to reduce the total required rendering speed or rendering throughput could leverage something that we've looked at and talked about last time, and all the way back to our color introduction lectures. That's that the photoreceptor size varies across the retina very, in a very extreme fashion. So again, this graph was retinal eccentricity is millimeters away from the fovea on your retina surface. And so at larger millimeters here, that's further away from the fovea. It means that it's in your peripheral vision. Wherever you're staring, it's off at an angle, okay, from it towards your periphery. In your fovea, which is the peak of this curve, the cone density again is super high, 150,000 on the order of 150,000 cells per square millimeter, and it falls off the density down to 10,000 cells per square millimeter or less as you get out into the periphery. So that's why when we look somewhere, if you really pay attention to your perception, you get a lot of detail where you're staring, and off to the sides, you get a lot less definition. Unless you look there, you can't read there, for example. So this leads to an example, to a simple idea in theory, but one that hasn't actually been deployed in practice yet. So this is an active area of research. The idea is called foveated rendering. The idea is that you track where the user is actually looking, so the eye motion, not just the head motion, and render the scene in the GPU with increasingly low resolution or low quality further away from the gaze point. So in other words, you start tracking inside the headset with each eye. Oh, where is the eye looking exactly on that array of pixels? And you render the location, or at where they're looking, you render it with a lot of full definition, full quality, and then allow yourself to render with lower quality and presumably higher speed away from it. There's actually headsets for which this is technically possible already to measure the eye location. The HTC Vive Pro Eye is a version of that. So this has an eye tracker inside the headset to track the gaze point of each eye. And this is a picture of foveated rendering. So you render a high-res image where the user is staring, in this case, the pink point depicting the gaze point. And then say this circle out here, you might render a medium resolution image, but at a much smaller size. So you can see this is a really zoomed in view right on this gaze point. And then for the full peripheral vision portion, you might imagine rendering this whole field of view here, angular field of view, as a low res image and try to combine all of these. You can do this, you can write code pretty easily to do this, but it turns out that combining all of these in some kind of reasonable way that perceptually looks reasonable and doesn't cause a lot of perceptible popping or tunnel-like vision or blurriness in the periphery, it actually turns out to be a bit tricky and is an active area of perception research. So a lot of VR research actually these days is not just on hardware, optics, or display of the design of the display rather, or not just on GPU rendering algorithms and things like that, but is actually in studying the human visual system, the perceptual system, in order to understand its characteristics in much lower level detail in order to be able to understand what the engineering requirements actually are. That's, I think, a good summary of where foveated rendering is currently or has been in the last few years. Here's another challenge. Another rendering challenge is that optical distortion is a really core characteristic of VR headsets. So remember, there's a display and then there's a viewing eye lens or an eyepiece, each for your left and your right eye. And it turns out, here's just a little photograph of that eyepiece in front of a display. The eyepiece being, a simple optical design for being lightweight and low cost is something that actually generates a lot of optical distortion. You can see it in this photo here, right? So it's a grid being displayed on some display in the background, and it looks like a grid pretty well in the center of this eyepiece, but towards the periphery, there's a lot of distortion. Okay, you can see it as a distortion of the grid. If you look closely, you also see there's chromatic aberration. So there's a separation between, you can see here, yellow and reddish fringes or bluish fringes, because it's a physical optical system, and there's dispersion, which, as you recall, is the property of materials that refract, like glass or plastic. Its dispersion is the property that when light comes in, the amount that it's actually bent, the amount of refraction, or the index of refraction, is a function of the wavelength, right? It varies with the wavelength. So being a real physical system, all of this stuff is occurring. And if you just render onto the display a view of the world that is rendered with the kind of graphics pipeline that we have talked about in class up to this point, and is the one that we use to render to 2D displays, it'll look like there's a lot of optical distortion towards the periphery, and it will spoil the sense of immersion for virtual reality. So instead, what you need to do is you need to account for this optical distortion and come back to the core end goal, which is for the user to sit in virtual reality and receive light from all these different angular directions to the eyeball that is as if you were sitting in that real 3D environment and looking out and seeing the color of the world in each of those directions. So in other words, you need to compensate for this optical distortion of the viewing lens while doing the rendering of the image for the display that is behind it. This turns out to be not too bad to do. I don't think I had this slide in the lectures that I used for the lectures on lenses these years, but most lenses have optical distortion, even photographic lenses that can be pretty expensive. So for example, it's very common to have, if you take a picture down in the Berkeley Marina, for example, you'd see that the masts of all the ships that should be straight lines, they aren't, particularly the ones in the corners end up being like curved lines. And that's because they're actually curved in real life. The boats wouldn't function very well if that was the case, but because of the lens, right? So this is kind of distortion goes by the name pincushion distortion or barrel distortion. That is, if you took a picture of a true geometric grid in the world, in the photograph that you get with a specific lens, what does it look like? And certain lenses exhibit pincushion, certain lenses exhibit barrel distortion. And if you calibrate it by taking pictures of, for example, real grids with those lenses, then you can try to remove that distortion through post-processing software to take the barrel and do image processing to realign the pixels to make it rectilinear. You can imagine how the process of how you do that. In fact, one way to implement this would be by texture mapping, okay, by mapping each of these locations in the photograph that you get through to a, like a rectangle that you draw that where each of the texture coordinates is remapped here in order to straighten it out. That should be a very fast implementation of this kind of distortion correction. This is exactly the same kind of distortion correction concept and geometry that is used in VR rendering in order to compensate for that eyepiece lens distortion. So basically, step one, you render the scene using a traditional graphics pipeline at full resolution for each eye. And then step two, you warp the images in a manner that the scene appears correct after the physical lens distortion. So basically, according to the geometry idea that I just described in the previous slide. In addition, see if I zoom all the way in here, you can see some of the details of this distortion. You can see that actually in the rendered image, in this case here, these are the rendered images that are put into the displays in VR so that when viewed with the optical viewfinder, it actually appears rectilinearly corrected for the person, right, that's looking in. You can see that additionally, there's color fringes in here. So what's going on there? The color fringes in here are appearing in the opposite order to the way that the lens is going to distort them, so that after being displayed, they'll align and this chromatic aberration will be significantly reduced from the perception of the user. So how does that work? Basically, you can render each of the RGB channels of this image independently, and you account for the distortion which will be slightly different. The amount of barrel distortion will be slightly different for each of these RGB channels, and you treat each of those channels and warp them slightly differently. A related challenge to this is that rendering via planar projection or via planar projective transforms, which is what we talked about in class in the graphics pipeline and the transforms lectures. That has problems in VR because of the very large angular fields of view that we already support in VR today, and we want to go much higher, right? Recall that current VR headsets are on the order of 100 degrees of angular field of view, but the human visual system per eye is something like 160 degrees, even without rotating the eye in the socket. So the thing that happens when you actually consider such large angular fields of view with a planar projection, like the simple linear perspective projection matrices that we studied in transforms, is that they really start distorting the periphery in a way that's maybe a little bit surprising. So here's a drawing, very simple drawing of all the rays that emanate to or converge on a point and from a plane, okay? And you can see that there's a bunch of little black lines that are drawn here in a dashed line, and they're all the same size dashes here, and separation is the same. But when they're projected down to a point, just because of the simple geometry of this, you can see that the dashes that are close to the center point of the projection here, the angular arrival here, they're much larger in angle. And you see that here compared to the dashes on the periphery, which because they're oblique, they arrive at the center projection point with a much smaller angle. And if you reason that out and you had a scene in which, for example, you had 6 red teapots that were all the same size and spaced evenly, and you rendered them with a linear perspective projection matrix, they would render looking something like this. The center one would be pretty skinny in comparison to the ones on the periphery, and the ones on the periphery would end up looking really kind of stretched out. Okay. And that's a problem in the sense that we're not using the bits of rendering in the most efficient kind of way, because you don't really need this additional level of detail or acuity in the periphery. So potential solutions for this might be to, instead of rendering to a flat display inside your headset, you might imagine having like kind of a curved display. Easy to say, hard to engineer. You might use ray casting to achieve uniform angular resolution instead of uniform resolution on a plane in this perspective projection. Another approach might be that you might try to render the world instead of with one projective transform and sort of one plane in the world that's being projected down. You might render it with piecewise linear projection planes, sort of break up the large angular field of view into multiple portions and render each of those separately with a different projection matrix that's tuned for it in order to minimize this kind of distortion loss. Let me show you a picture of that. It turns out that that last solution I described is one that is used in quite a number of current headsets. It goes by this name called lens matched shading, which is a bit of a funny name, but if you're interested, you can search for that and sort of get tied into this. The idea is pretty simple. So if you look here, this is a large field of view image that has that problem I described before, where it's pretty distorted in the corners. They get really stretched out, and small objects get really, occupy a large number of pixels there. And we compress the scene in that periphery to use fewer pixel samples there by drawing an image that looks like this. This is sort of the geometric description of this projective transform. So instead of having just one single plane in the world that we're projecting, we draw 4 images. We render the scene in 4 different quadrants. And in each one of them, we tilt the plane so that it projects in a more rectilinear fashion into that angular field of view. So the resulting images look like this, and then you would distort them back into this original image if you want, but you would have fewer pixels in the periphery, so you wouldn't be over generating definition there. Hansung has a question. Related to the mention of ray casting, is full path tracing also used for VR? I can imagine rendering latency for ray tracing is even higher than traditional rasterization as of now, but if there is higher demand for visual quality in VR, could ray tracing be a good choice? Yeah, this is a really good question. And I don't know the answer off the top of my head, but I would suspect that because ray tracing has received so much attention recently and so much optimization through APIs all the way down to silicon acceleration, that there are certainly applications in VR that are making use of path tracing like solutions, or at least ray tracing solutions, in order to do rendering. And I think you hit the nail on the head that in general, it's still more expensive than rasterization-based graphics. So for a lot of applications, still rasterization-based graphics, are for sure dominant, are for sure a really important engineering choice for VR, VR applications. Okay, next rendering challenge. This one's an interesting one, and you might have to put your thinking caps on to look at some new graphs, some new space-time graphs, and follow on with some reasoning here. I want to teach you about some of the key perceptual artifacts that occur uniquely in virtual reality rendering, and they relate to the fact that the challenge is eye motion in the presence of finite rendering rate. I didn't frame the next few slides in terms of sampling and aliasing and things like that, although there's certainly a way to, that would be a very valid way to try to analyze this, what's coming up next. But I focus instead on the geometry and understanding what's going on geometrically in space-time. Okay, so what do I mean by that? Let's look at an example. Okay, let's consider comparing what happens when you look at a candidate world. We'll do some really simple worlds where there's just like a red ball, basically, and we'll consider it moving in different ways and whether how our eye is moving or not to track the ball, basically, over the next few slides. And we'll compare what is happening in reality in terms of the space-time diagram of the light that arrives at the eye versus what's happening in virtual reality, where we have a discrete and finite refresh rate on the display. Okay, so let's look at this first example. Here's an eye, it's looking out in the world, there's a red ball, as I mentioned. There's some X here, okay, which I'll describe in detail a little bit as we get into this example. Let's consider what happens in reality first. Okay, so here's a diagram for something that's happening. X here is the position of the object, in this case, just the red ball, relative to the eye. That's key. Okay, so let me say that again. It's the position of the object relative to the eye, and time is extending, passing as we go down the page here. Okay, and in this particular situation that I'll give a name to and a description for in 1 second, what's happening is that we're seeing a red ball or a red object at a fixed X position all the way through time. So what could that represent? It could represent, it turns out, a few different things when we consider VR systems, but in this case, let's assume it comes from the situation where the red object is fixed in the world, and the eye gaze is also fixed, okay? So in that case, the X position of the object relative to the eye is at a particular X location that's not changing in time. Simple case, just to warm up. What's happening in VR? So let me introduce the key features of this VR diagram. Okay, so there's going to be frame 0 here. It's at a finite refresh rate. So what's happening? It's showing you a red ball. The red ball is appearing on the screen. Your eye's not moving. The red ball's not moving. So you just see a red feature at the same location X, for the entire frame. Same for frame 1, frame 2, frame 3. Really simple. In fact, nothing happened. And in fact, it looks exactly like the real world continuous case here. Okay, so this is good. In this case, when the eye is not moving and the red object's not moving, things are fine. Now, what happens if the object is moving relative to the eye? Okay, so in this case, the X position is changing, the eye is looking in one location, and the red ball is moving. So in this case, the red object happens to be moving from left to right while the eye gaze is fixed. What happens in VR though? So we sample the location of the red ball at the sampling time for frame 0, and we draw it on the screen, right? We get a picture of the red ball at a particular location. So we end up with one spot here. And at frame 1, it's moved over. Frame 2 is moved over. Frame 3 is moved over. So it's kind of a bit of a difference here, right? In the space-time drawing of where the light is coming from and going to the eyeball here. Pretty big difference. So is this a problem? This is the effect of time discretization, but it turns out that this actually looks fine, okay? This is, if you reason about it, this is the same perceptual effect that you would get if you just saw a red moving ball on a regular 2D display, okay? So anytime you see a movie in which you're looking at one location and some kind of red ball moves across the screen, you would end up with a space-time diagram that looks very similar to this. And we don't really have problems with that when looking in normal displays, and you wouldn't really have a problem in the same way when you're looking in VR. The problem that occurs that's unique to VR is this next one. Okay, so let me show you what happens. This is when, case 3, the eye is moving to track a moving object in VR, which of course is a really common situation, right? You're looking somewhere in the world and then a red ball moves through, and instead of moving your head to track the object, first your eyes notice it and your eyes start rotating in your head in order to track that moving ball. That's the sort of situation we're talking about. So here, the red objects say moving left to right, and the eye gaze is moving left to right to track the object. So what does that look like? It's the same diagram as before. For the continuous case, the position of the object relative to the eye is a fixed X, right? Because it's moving, but the eye is also moving with it. So it stays at the same X location in the eye for all time. But what happens in VR? So this is the place where we have to reason it through. This happens for frame 0. What happened there? Well, again, so we sampled in time. We got a location for the red ball. we drew that picture. Okay, so we have a picture in which the red ball appears at a particular location, and it's displayed for the whole frame zero duration. While that's happening in VR, though, our eye is tracking the movement of the ball, not within the frame, but over different frames. So the eye is moving to track that moving ball, but while it's displayed statically for the duration of frame zero, our eye moves, and that momentarily static red ball is now slipping across our retina. Because our eye is moving left to right, the appearance of that ball is moving right to left. And what happens at frame one? Well, actually, it turns out the same thing happens, because now our eyes move to a new location. The ball has moved. So the rendering of that frame had the ball at one location for frame zero, and then at a new location for frame frame zero, now for frame one, our eye is still moving across it though, right? So the frame, again, the ball is displayed for the whole of frame one, and exactly like in frame zero, eye moves across it and repeats this pattern. That happens again for frame two and again for frame three. So remember, we now have a sequence of 4 video frames where the red balls are appearing in one location, 2, 3, 4, our eyes moving continuously across it, and this is the space-time diagram that results. Following me? Okay, so eye is moving continuously relative to the display. During each frame, the image of the object is lagging behind the eye motion, just for that 1/90th of a second. And the space-time diagram looks like this. This turns out to be not okay perceptually. Okay, it looks really bad. And you can think of it as a smearing and a strobing effect. The name that's often given to it colloquially is called judder. Okay, so this is visual judder in VR headsets. And it's kind of perceptually unacceptable. You can't ship a headset that has this effect. So what are some solutions for trying to reduce judder? Let's talk about a simple concept, right? Okay, so this is some variation in X, and for a certain frame rate, if we could increase the frame rate, say we could double it, okay, then it's going to get better, right? Because we'll double the frame rate at which we're drawing that red ball. It'll move a smaller amount in each frame, and our eye, as it's slipping across, is going to have this judder smear halved, okay, in X. Yeah, this will really help. This will halve the amount of judder, but it's expensive, not just because you have to increase the frame rate twice, but everything in the system needs to increase. You have to put out that light refreshing hardware at twice the frequency. You have to render your GPU at twice the rate, right? Twice the bandwidth, so on and so on and so forth. But it will give you a closer approximation of the ground truth. Good in theory, very expensive at a system level in practice. So it turns out that in contrast to this solution, the approach that was used investigated, designed, and is the common one in VR headsets today is to use something called a low persistence display. This is the space-time diagram from it. Perhaps you can already interpret it and tell what it means, but let's go through it, okay? In a low persistence display, the key idea is that the pixels physically emit light for a very, very small fraction of the frame duration. They don't put up a picture of a red ball and keep it up there for, say, the whole 90th of a second, if it's a 90 frame per second display. They only put it up for a flash. So they flash the picture of it really brightly, and then it's black. And then 1/90th of a second later, at frame one, they flash it again, and so on and so forth. What are the numbers of this? So in an Oculus DK2 OLED display, it used a low persistence display. At that time, it was a 75 frame per second refresh rate, which means there was about 13 milliseconds between refreshes of the render. And the pixel persistence, though, so the amount of time that the light was on, was much shorter. It was like 2 to 3 milliseconds only. Now this reduces judder, right? Because in this case, the light that is appearing and relative to the eye motion is going through this space-time pattern here. And that doesn't happen in the low persistence display because it's only turned on for this brief flash of light. So your eye just sees it in one location fixed in space. Morgan asks the question: do they try to synthesize the background of where the ball is with the surrounding pixels, or is it just black? Try to synthesize the background where the ball is with the surrounding pixels, or is it just black? Yeah, great question. They definitely render the background too. So this is a very simplistic scene where there's only one red ball, okay? So just so we can draw the space-time diagram in a way that, is simple here. For general scenes, they would draw the whole world, including the red ball. If the red ball is moving, then that's the only thing that's moving. So the part that's black is not appearing spatially. What's black is that instead of putting up that picture with the red ball in it for a whole and keeping it illuminated for 1/90th of a second, in time, it's brought up really bright, but flashed, and then the display itself is putting out no light for most of the rest of that frame. So in this case, for something like 10 or 11 milliseconds, the display is black, and then for 2 or 3 milliseconds each frame, it's lit up brightly. Okay, but with a picture that includes the background and the red ball too. Is there a perceptible flickering with these displays? Yeah, great question. No, because of fusion of vision, this kind of frame rate, and this kind of refresh rate, 1/90th of a second is fine, and it looks totally temporally continuous. Good questions. Now, kind of related problem, sort of related, but a little bit independent too, is another problem in this area that displays in VR can exhibit "quote unquote" rolling shutter artifacts. If you reason about it, actually, this can occur with regular displays too. It's just that you never move your eyes over a regular display in a way where this becomes typically a problem. So it tends to be more in VR. So what's the problem? It's actually not a rolling shutter. That's why I just put it there in quotes, because we study rolling shutter artifact when we talked about image sensors and the way that it arises, the reasons for it. And in displays, it's really more like a rolling backlight is maybe a more accurate way to describe it. But mathematically, it's for the same reasons as rolling shutter in sensors. The problem is that the pixels in these displays is illuminated from top to bottom sequentially in time. It's because they have to refresh the memory, and that's a sort of sequential process for driving each of these things. And then they have to sort of signal each of these locations in the physical array of the display in order to turn on and off. And the signaling is sequential. So light emitted from the bottom row of pixels is going to be turned on and arrive at your retina later than the top. Light at the bottom of the frame arrives late. If your eye is not moving, okay, this is not necessarily a problem. You won't notice it at all, but your eye does move inside the headset, staring at different parts of the headset in VR. It's sort of a core feature of VR, okay, that creates this sense of presence as your eye roams around and then your head moves around, and you coordinate all of that in your normal gazing patterns within that simulated virtual world. When you do that and your eye is moving against the display, if we don't compensate for this problem in the first bullet, or this feature described in the first bullet, then it will lead to perceptual artifacts that are similar to the rolling shutter artifacts in cameras. For example, there's a whole range of them depending on the eye motion. But for example, a VR image may appear horizontally sheared. We've seen examples of that in rolling shutter. It's almost like you took a photo and then you like knocked it over to one side. It may perceptually appear like that in VR if the head is moving, for example, from left to right. Okay, so that's a fact, and you can sort of try to reason out why that happens from your knowledge of rolling shutter and using like the space-time diagram analysis that I showed in the last few slides. How do you fix it? How do you try to fix it? Compensation techniques might include, for example, you might perform a post-process shear on the rendered image. You need to know, though, you have to be able to estimate the eye motion in order to try to do this in the correct way. You might, if you know all of that, you might try to render each row of the image at a different time, the predicted time that the photons will arrive at the eye, realizing that the display is going to physically emit the light for each of those rows at different times. So maybe you'll render them at the appropriate time, sort of just-in-time rendering, if you can imagine it that way. That might be really amenable to something like a ray tracing solution, where you have a 3D world that is undergoing animation as a function of time, and you can trace the rays by tagging the time associated with each ray as a function of the location on the screen as well, so that you render at the bottom of the screen into the 3D world that has advanced in time a little bit. So this can sometimes be a good fit depending on the software architecture for ray casting as opposed to rasterization. Next rendering challenge. High quality versus low latencycy resolution. What's the problem here? High quality rendering can be slow, okay? Constraints, you got a battery powered device, you got high resolution outputs for both eyes. Already in the comments today, Hansung pointed out, well, maybe you want really high quality in VR because you're trying to immerse in a virtual world. So maybe you want path tracing, which is also expensive. That can add on there too. The implications of all of this is that it can take significant time to render a frame with these, battery power constrained GPUs as fast as they are. It'll take time, and this is going to increase latency, right? So if you get the whole world sort of set up and you say, okay, let's start rendering now. If that takes you 1/90th of a second, then that falls directly to the latency, right, that we talked about earlier. It's going to increase the latency by a full frame, which is a lot. And that can very easily add to the motion sickness problem of extending that latency and decoupling the reality of, or the rigidity of the world relative to what photons are arriving at your eye. In fact, high quality rendering could be so slow because you want such high quality that it could reduce the frame refresh rate. How does that happen? If your system is running at 90 times per second refresh rate, but your rendering time takes approximately 1/90th of a second, sometimes maybe a bit more than 1/90th of a second, then the frame rendering time might be longer than the refresh rate. You may not have something to refresh at 90 frames per second. All of this adds to a pretty big challenge. And in order to try to maintain that ultra low latency with respect to that issue of that we talked about earlier, end-to-end latency of that three-dimensional illusion, in the constraints of you want to do high quality rendering as well, a modern VR engineering solution is something called reprojection. Pretty simple idea, but let me try to walk you through it, okay? So the idea is to decouple the slow, high quality rendering of frames from a fast reprojection algorithm that will happen immediately before the display, like very, very immediately before the physical display of light. The high quality frame can use, whatever head tracking is available when it kicks off its high quality render, being totally fine, accepting the fact that that head tracking information may be kind of old or stale by the end of the render because it's a slow render. Reprojection, though, is going to start and finish extremely close in time to when we emit the light. And what it does is to take the most recent high quality rendering and then warp it, okay? And warp it using the very latest head tracking data. So it says, hey, the GPU rendered something at real high quality using that assumed head tracking data. Now I know the head tracking data is updated to this thing. How do I take that render and then warp it in order to make it as close as I can to what I would have gotten if we use this head tracking data? And then I displayed that right before. This warping algorithm can be very lightweight and extremely fast. So therefore very low latency. And then you use this, at a very fast refresh rate. The accurate reprojection warp here requires, the rendered image. You need at least the depth map associated with that image. And you could potentially also use motion derivatives like optical flow. Oh, I missed a bullet point here, actually. I must have edited it out. The other thing is that also if the high quality frame is kind of slow, so if it was running and maybe running at only refreshing every 1/60th of a second because it was trying to do so much fancy graphics that it was kind of running slow, the reprojection can occur though at 90 frames per second, right at the refresh rate of the display. And it can just reproject from the last available, high-speed render. So if the last high-speed render was the same as the one it reprojected last time, fine. It just still uses that. It reprojects that twice, right? But it will still track the head tracking and use the latest head tracking. So what does this reprojection warp look like? Let me just give you a picture to give you the high-level idea. So here's a picture that has an image. There's also some kind of depth map that's not drawn here, but just think of it as like, there's a Z buffer associated with this. And then there's little arrows that are drawn here, which are the reprojection. Okay, so it says if we take this image and we reproject each of these pixels from the head of the arrow to the tail, from the tail of the arrow to the head of the arrow, and we move those pixels across, you can imagine using a texture mapping function in order to try to do that. Then we'll get an image that is as if we moved our head a little bit to the left here, okay? And that's exactly what happens in this reprojection algorithm. It turns out if you also had some information about the fan blades, maybe they were spinning here, that's what's depicted here is if you, in the rendering, high quality rendering, you also store some of this optical flow information, the reprojection algorithm can also take that into account. For example, if it used the same frame but reprojected it twice, as I described earlier, then this optical flow would cause the second frame to look as if the fan blades had turned a little bit. Of course, you'll end up with additional, increasing visual, pixel artifacts as you do that in this reprojection. So it needs to be, pretty short in time, but that tends to work out pretty well because the deviation between different rendering frames is actually pretty small. Okay. So that's a blitz tour through a survey of different rendering challenges that occur in virtual reality and sort of some of the core issues that come up, specifically revolving around latency and things like distortion caused by either the physical hardware or eye motion relative to the display, and the kinds of engineering issues that VR graphics engineers have to think about in trying to ameliorate those kind of problems that occur perceptually by clever rendering hacking, basically. The last topic that I want to talk about VR and share with you has to do with VR imaging, okay? Now, at a high level, the idea of VR imaging is really easy to say, but let me just qualify this up front by saying, I think this is the area where, things are least developed for the VR, technology ecosystem. There's lots of research in here. There's lots of sort of demo systems, but it's really not any baked practical solutions like we have for regular 2D displays. For regular 2D displays, we all have cameras, okay? We've had cameras for decades, and in our smartphones, they're so optimized now. You just take a picture and you can create a 2D little window of a picture, on your phone, on the display, on any display on the internet. It looks great, very high fidelity, very well understood. In VR, what you want to be able to do, I guess, conceptually, is have a camera that you can click somewhere in the real world and then be able to transport that three-dimensional world into VR so that you can replicate the experience in VR. But the VR experience is about immersion in that 3D world and to see it in stereo, right? To see with the left eye and the right eye with different perspectives, to be able to move your head as you normally do, and that normally in VR would give you a sense of head parallax by very slight changes in perspective of all the objects in the world as your head tracked position is used to render all of that. All of that works with graphics rendering because we have a full 3D model of the world, and all of that re-rendering just occurs by small changes in the linear projection matrices or camera viewing matrices that we have talked about in the graphics pipeline and transforms lectures in class. So all that works great. VR imaging, the problem is that those kinds of things like head parallax and stereo really don't come easily. And my main purpose in the remainder of this lecture, in this portion, is to try to give you some intuition for why it doesn't work and some pathways to how we might be able, or how people are trying to solve that today. Okay. All right, let's get into it. So what does work in VR? Spherical imaging. We'll call it monocular 360, which is how it's sometimes referred to. Spherical imaging works in VR, but it is not a full VR imaging solution, as I want to try to help you understand intuitively why. Okay, but first, what works? Things like a spherical camera, you might have seen these, is like dual fisheye cameras. You can buy this for a couple $100 now. It's a Ricoh Theta. So what does it look like? You can see here, it's got in profile, there's two bumps. These are two fisheye lenses on it. You click a picture or even turn video recording on and just move it around, hold it above your head, move around, and you get a capture of a 360-degree video that you can absolutely play back in VR. And what do you get? Well, actually, I don't have a picture that shows that. What do you get? You get an experience where you're watching a video in VR and you can look anywhere. So you can look up, you can look backwards, you can look down, you'll see all the kind of right things. Now, with this Ricoh Theta, there's some practical challenges. Since it's 360, you'll see the hand of the person that's holding it, okay? You'll see the top of their head probably, or a tripod that's holding up, things like that. But, aside from that, you get a pretty good rendering in 360 of the environment that this is in. And if you stuck it on a moving target, like the headset is someone riding a BMX bike, for example, that content looks amazing, and at 360, it's very compelling. So that works great. Let's get into some nitty-gritty technical details though first. Okay, so a couple of things. This is more like a nit, okay, but interesting to talk about because you have a lot of knowledge from camera imaging systems and centers of projection and the rays that pass through lenses. So what's the problem with the RICO theta? Technically, you want this ray sampling. It's as if you have a single center of projection and you want all the rays of light that pass through it. That's a spherical 360 image, okay, a perfect one. In the RICO theta, you have two lenses that I'll approximate by having the thickness of the camera between them and two centers of projection. So at best, you get this kind of ray sampling pattern with this gap in between. Now, you might say, well, I don't know, that seems pretty close. The RICO theta is not that thick, which is true, but you have to stitch them together, and you will get a seam at this boundary between the stitching of this camera to this camera. It can be made to look pretty hard to see for content that's far away, sort of at infinity, but you can persuade yourself, I think, that if you had someone standing pretty close by, the thickness of this lens, which might be, say, the thickness of someone's nose, if they're standing pretty close by, those rays of light might have to chop through that face, and you might lose some content in between that thickness of those centers of projection. So for content that ends up being portions of the scene that end up being close to the camera, this stitching problem inevitably will create some kind of artifacts. But in general, you can try to minimize that as much as possible. And as I said, they can work really great for lots of use cases. Just very briefly, there have been other methods of trying to capture spherical data. This is another approach. This is a spherical camera from a company called Panono. Again, you want this ray sampling. In this case, you get this ray sampling. And this is sort of a bit of a trade-off if you want to try to approximate this. It turns out this might be useful for other things. I'm going to return to this later when I talk about modern VR, current attempts at trying to do high quality VR imaging cameras. Still very much at the research phase, but keep this sort of picture in mind. We'll return to it later. How does high quality stitching work as a solution? You can do a better job if you use computer vision. So use computer vision techniques like detect image features. Image features are like detect an eye, like an inside corner of an eye, or say the tip of my collar, those kinds of visual features in each of the camera views. You can use something called like SIFT, which is a common computer vision algorithm in order to find these kinds of visual features in multiple images and correlate them. Correlate them across frames and do geometric transforms to bring them into alignment, and then warp to align all the frames and blend them together. This is easier said than done, but this is sort of the basis for creating high quality or the highest quality content of this kind that can be created. That's 360-degree imaging, or 360, or just spherical imaging. But that's for one eye, right? In the thing I just described, you only have one RICO theta that's producing one video, and we're going to play back in both left eye and right eye. So you don't have any stereo effect if you look at this in VR. Which will look a little bit strange. You get used to it. It looks okay, but you're not having any stereo 3D effect. How can you try to get that? Well, that would be like spherical stereo imaging. So this would be sort of one step up, still not really full VR. That's where we're sort of headed in this progression, but spherical stereo imaging is an interesting goal. What does that look like? What pairs of viewpoint positions do we want to sample? So this would be as if, okay, if you conceptually think of someone sitting at one position in space, and all they do is sort of they rotate their head to look at different, look at the world in 360 from different directions. What is the sampling of rays that you want to collect? And what's shown here is in red, the space of rays that you'd want to render into the left eye, and joined by a black line in blue, the set of rays that you want to render into the right eye in order to create the stereo image pair to the left and the right eye for that viewing direction. And for different viewing directions, you can see it's a different set of rays. This is kind of the problem. It's quite a bit different than the ray pattern that we looked at for, let me just bring it back up. Okay, for monocular or one eye spherical imaging, it's just this set of rays, this black set of rays that we want here. When we went to stereo, you see right away that you actually kind of need like a much, much larger set of rays. So what is a parameterization or an organization for this set of rays that we need? one idea is to conceptually spin a pair of cameras about a midpoint. Okay, so you could take these two cameras here, or spin it around, put two cameras separated by this distance, and then conceptually spin it around. This doesn't give you full spherical, right? Because it wouldn't allow you to look up, but it would be as if you sat and you, in one plane only, could turn just, like vertically spin your head around like an axis, a y-axis through your head. So you could look around in all directions. Okay, so it would give you that. Now, it turns out to be a lot of data. I don't want to get too far into the details of what I'm going to talk next. So think of this more as just like a bit of a like a FYI on some stuff that people have tried to take this large amount of data and then compress it with approximation and loss in order to try to be able to make stereo, VR, something that you could even put out into consumer products. One attempt is something called omnidirectional stereo. So instead of, full frame left eye and right eyes, you approximate this set of rays over here by this set of rays here. Okay. You see what happened? Like the origin point of each of these rays is slightly different. They're not all located at the same location, but it might be okay. You can sort of try to figure out when it'll look wrong. It turns out that if you did this and you just use this is called an omnidirectional stereo approximation. And the set of rays that you need to store looks like this, which is a lot less data than before. And it turns out that you could analyze this further and convince yourself that this could come from, come from, how do I put this? Like if you had a camera and you spun it around in all directions, so you captured that video, you could get the omnidirectional data just by pulling out one row in that video, and two different rows would give you the two different set of rays that you need here. Okay, anyway, I don't want to go further into the details, just to give you a flavor for how some people have tried to take the sort of unreasonable amount of information that you need to store for omnidirectional stereo as an extension to a video format and bring it something closer to something that's practical. It turns out that all you do is store two like wide angle video, two wide angle videos. And by sampling from those appropriately, you can generate this omnidirectional stereo. This is actually deployed in things like YouTube, YouTube VR, video formats. So the approximation to try to make this practical is something that has received a lot of attention, and this is one of the current attempts. Okay, I don't want to belabor this too much more. This is what it sort of looks like for some tour examples, left eye and right eye, and you can sort of analyze the cases where the errors are largest, which I'll sort of leave here. I don't want to get into those details further today, but now you've heard of it. Now, again, you could render that data and you could compress it, but how do you even go about capturing the data for this, for this omnidirectional stereo thing? The thing I showed before actually means you have two cameras sitting on like some kind of rail and you spin them, okay? And something you spin them really fast in some prototypes and capture a lot of video data in the subsample. It's kind of pretty hard actually and unwieldy to use all of those. A different approach that sounds really appealing, but it turns out I want to share this with you to show you why it really doesn't work easily. And you can work really hard to try to make it work, but there's a lot of sort of trade-offs and a lot of artifacts that occur. The idea might be like, well, we've got two eyes. If each one was a spherical camera, couldn't we just have two spherical cameras? Wouldn't that be enough, right? Isn't that all we need, a left eye and a right eye spherical camera? This is a research paper from SIGGRAPH 2017 that looked at this low-cost 360 stereo photography and video capture. So that's exactly what they did. They just bought two Ricoh Thetas, stuck it on an aluminum rail, and tried to say, "Hey, can you produce good spherical, stereo spherical video with this?" The problem, which is what I'm trying to build your intuition for here, to understand the difficulties involved with VR imaging in general. So what's wrong with this solution? First of all, let's start with when you get it right. Okay, so if you just have the left eye and the right eye from the theta on the aluminum rail and they're both looking forward, say, If you sit in VR and orient your head along in the direction at which the two cameras are pointed, where that's the aluminum bar joining them, you'll get exactly the right answer. Okay. Why does that happen? It's because the separation between the left camera and the right camera for that pointing forward direction corresponds to the separation in perspective that you want to give the left eye and right eye for the person that's staring in that direction in VR. Okay, so you end up getting exactly the right data. You don't see the whole spherical data because the person can't see the pixels, the rays that come from the background, for example. So you pick out a subset, right, of the Ricoh camera spherical views and present that to the left eye and right eye only, approximately 100-degree field of view. You get that perfect. The problem you can see is that if the person starts to rotate, and so this is a top-down view, okay, on top of the aluminum bar and the left eye camera and the right eye pointing forward. So if we are in that top-down view, consider what happens if we want to, let me just make sure I can remind myself of which one is which in this diagram. Okay, I got it. This is the viewer in VR. They've rotated their head now, so now they're looking in this direction over here. The separation that they want between the eyes is the same, right? Because it's the separation in reality of the person's head. So that separation is the same. And you want the rays, for example, that point in this direction and this direction at this physical separation. If you just go to the left and the right cameras for the Ricoh theta and pick out the pixels that point in that direction and that direction, you can pick them out no problem. The problem is those two rays correspond to a separation that you can see by the diagram here is smaller than the true separation that you want. How much smaller? It turns out it's smaller by a factor of cosine theta, where theta is the rotation angle there. Okay, and that cosine theta ends up being very problematic. Let's just draw it out. Okay, so what happens if by the time the person is rotated and is facing exactly left and right, you'll see that the two rays from the right and the left Ricoh cameras, or the left and right spherical cameras, are now pointing in exactly the same direction. So the disparity is the physical separation between those two views. The disparity is now 0 when we wanted it to be B. Oh no. Let's keep going. If you keep rotating and turn around and look backwards, by the time you look backwards, the left eye and the right eye positions have flipped, right? They're now on opposite sides. So in VR, the person is looking backwards. If we just took the ray from the left eye and the right eye the left camera and the right camera and continue to try to show those to the VR viewer, they're not actually completely reversed. The left eye is getting the picture from the right separation, and the right eye is getting the light from the left separation. So it's like actually inverted stereo. It'll look completely, completely wrong. It'll be uninterpretable. It'll be perceptually very strange. And that's exactly what happens if you do the naive rendering of just taking a left and right spherical image and just trying to look up into those to present the left and the right eye with the information they need in a VR headset. This sort of graphs the disparity variations I just talked about. And if you're interested, you can take a look in this paper or look at these graphs, which I think are pretty self-explanatory, but I don't want to go into it further because I described the main effects that are going wrong. There's one other problem is that, first disparity, the incorrect baseline that you get as the view angle changes. The second is that you have occlusion. You have these two cameras, they can both see in all directions, and each of them is seeing in the other. So if you look in their videos, you'll see the left camera in the right camera view, and the left camera will see the right camera in its view, which is kind of a problem. So you have to sort of delete them and sort of hole fill that part of the camera. That's another practical problem. So the solution that is put forward in this paper and is studied in this line of research is computational photography. So what you do is you try to take the two stereo views and use computer vision to estimate a 3D reconstruction of the whole world. It turns out the stereo reconstruction has gone a lot better in computer vision, but nevertheless, only from two views, and two views that are kind of not separated that far relative to their angular fields of view. It's getting a bit technical, but it's not the best data from which to try to do stereo estimation, it turns out. Anyway, you could try to do it using computer vision. You'll get something, and then you could try to correct the disparity problem that I described before by using not directly the pixels in the left eye and the right eye from the left and right cameras, but rather to try to re-render the world with the left eye and the right eye and say, oh, what would have the colors have been from that 3D world if I had rotated these two views and rendered it. Turns out that that will reduce to trying to amplify the horizontal disparities by 1 over cosine theta, and to avoid this flipping left eye, right eye problem when you're looking backwards instead of forwards, things like that. But maybe a conceptually simpler way to understand it is to take the two views, estimate full 3D of the world, and then from that kind of apply graphics, okay, to render the views instead. And you also have to do hole filling. We touched on this a bit in image processing, and I talked about one method. This is a deep topic in computer vision, but how do you cut out the view of that camera, right, of the other camera from one camera's point of view, and then how do you fill it with data? Fortunately, you have the other camera's view, so you can be a little bit clever about it. You can try to do as best as possible, but you kind of need to make up the data a little bit inevitably in this solution. If all of this sounds like a bit of a mess to you, it kind of is. It's kind of ad hoc. You don't have the right data. You kind of have to make some of it up. The benefit, though, is to try to get a stereo camera setup that is as simple as having just a VR camera setup, rather, that's as simple as having just two cameras. So try to get it with the simplest camera, but the results are, have trade-offs, and it requires a lot of kind of pretty hokey image processing and graphics processing. This is an example of a spherical stereo result. It's kind of a bit hard to interpret. It's drawn here in red-green stereo. It's kind of hard to interpret without actually putting it into a VR headset and taking a look at it. It's not bad. They did a lot of hard work, and the results are sort of reasonable under certain circumstances. But if you tried to do it with video and people started moving closer and further, there'd just be a lot of sort of artifacts that are pretty visually apparent. Okay, so where have we gotten so far? We talked about spherical imagery, monocular. We talked about stereo. So how much harder that is actually already in storing a lot more data, it turns out. And then if you try to capture real cameras, some real hard problems. You might have to have spinning camera systems spinning really fast, or trying to make them simple and doing a lot of hard work in graphics. But we're not even anywhere close to the full sort of experience in VR yet. All we've got so far is an attempt to try to look in all directions and see that in 360 and maybe with stereo, but no head parallax yet, no immersion in the sense of if I'm in VR and I move a little bit closer to or further from objects in that space, that I would feel as if I'm moving closer to and further away from them visually by immersion. We don't have any head parallax information in VR imaging yet. So moving viewpoint imaging is what I want to talk about next. This would be sort of full VR effect, full planoptic function would be another way to talk about it. What is the planoptic function? Planoptic function is a fancy name for some things that we've talked a lot about in class already. The 5D planoptic function is some function of, say, the amount of light traveling along or measured at different points in the scene, measured at, say, a viewing position in XYZ, say like at the center of each of these balls that's drawn in the middle of this, sort of garden here. And then in every direction, theta phi. So pick a point in the world, XYZ, and then think of a direction of light, arriving at that point from theta phi, and say how much light was traveling along that ray. That is the 5D planoptic function. The 4D light field, which is something we've talked about more, is it turns out that the 5D function Vx, Vy, Vz, P theta, P phi will become same as, sorry, there should be a Vx, Vy, Vz here, same as this light just given a four-dimensional parameterization of a light field, as we've talked about elsewhere. Because if it was just like in this picture here, where it's like just on a grassy field and it's just all in air, then because we've studied that the light is preserved along a ray, then although the planoptic function is five-dimensional, one of the dimensions is redundant, because you're going to get the same value of light for all the connected points in the world, all the XYZ positions, that are connected by a ray passing through them at a particular trajectory. Okay, so one dimension comes out and you can reduce it to a four-dimensional light field. This presents an approach of trying to capture the totality of light change in the world. That's where these ideas of like light fields and planoptic functions theoretically arose from people, researchers trying to reason about what is the total information content, what is the dimensionality and the functional structure of all the variation of light in the world. If you captured all of that as a function, then you would be able to render it in something like a VR system and fool anyone into thinking that they are moving around this kind of a world by just figuring out where they are and then putting the light into their eyes that corresponds to the sampling of this light field or planoptic function at those eye positions. This is all very theoretical to try to understand what the full nature of this light is. The next question then is, can you build camera systems in order to try to sample this function at the required resolution and accuracy to display it? I talked about this in earlier lectures, sort of a robot that you could imagine, a prototype research system to try to put a camera at every point on a sphere looking inward at an object to try to take pictures of it from all viewpoints. We talked about light field cameras in arrays of them, multi-camera arrays. I didn't show you this picture, but this is a result from this kind of a multi-camera array that's more relevant for VR. Excuse the quality of this video. This was created back in 2005. And so it was a much more research grade system at that time. This is someone that's going to be heading a soccer ball while standing in front of this light field video camera array. And what you can see is, okay, the person is going to head the ball, but you can also pause in time and then change the viewpoint as you saw there. So you have sort of free viewpoint change. And you can move it not just left or right, but using VR rendering, you can actually fly into closer to the person further, and you see all those kind of perspective changes as well. We talked in the light field camera lecture about how geometrically that's quite related to like a planoptic camera. So even from a planoptic camera, it turns out you can get a bit of this parallax, side-to-side eye motion relief. So here's a rendering from a light field Litro camera. Each of the following is a single shot. It's not like a video sequence. It's one shot from the light field camera, and then we render different viewpoints and focus changes. So changing the focus to this bird in the background, but you can sort of see the parallax changes that are occurring of the boat relative to the background. Refocus to this boy. This one you can kind of get a sense of the parallax more over this crowd. You can get a sense of change in perspective to get higher or lower. That sort of parallax change. Small in this case because the light field entrance area right over the area of this aperture of the lens is pretty small, just like a tens of millimeters. So what I want to talk about next is that light field cameras in principle capture the kind of dense sampling of rays from which you can try to do re-rendering and could be the right kind of idea, like arrays of cameras in some sense are theoretically the right idea for capturing the raw information from which to do VR, VR cameras and see the content in VR headsets. But the configurations as we currently have them, only the light field from over this small baseline here or over an array that's pointing in one direction are not geometrically quite right. So you might sort of try to need to make new cameras that have them in different sort of position differently spaced, maybe like on a sphere. I'll come back to that in a second. But before I get to that, I want to touch on a key problem, which is resolution in this light field space, in this ray space, if you will. The camera arrays that I've talked to you about have like on the order of 10 by 10 views. I said 100 camera array. In a light field camera, the array of views that we had here, it turns out it was 14 by 14 in light field camera. In any case, okay, these numbers are pretty similar, 10 by 10 and 14 by 14 views. How close is that to the density of views or the number of different viewpoints that you need to service, VR imagery in modern VR headsets? That's sort of a question. I want to try to give you a bit of intuition about that. Before I do that, I just want to replay this video to get a sense of like the most challenging cases, which are when you're very close to content in VR. It turns out that's going to be the case when the amount of camera information and the density of information that we need in this sampling of different views, different camera views, is going to become really difficult, really high, really expensive. So let's just remind ourselves of the intimacy of VR. Okay, so here again, The reason this case is really intimate is it's an artist drawing content, and this artist is immersed inside that content. You see here, you're just like millimeters away or centimeters away from that content, and tiny movements of your head, you can picture this, are causing really large perspective changes, right, on that volumetric structure of this artwork hanging in space. But it turns out that the challenge is just there in general. VR is an attempt to virtualize worlds. We want to have intimate experiences in VR. So imagine the intimate experience of trying to have like a child sitting in your lap in VR. That's very close proximity. How dense do you need the camera views to be in those situations? Now, how dense are camera views today? I said, multi-camera arrays, 50 to 100 views, planoptic cameras, 100 to 100 views. The views, again, are right these things here, like how many independent viewpoints are being sampled. Now, contrast that with how dense must the camera views be in VR in order to create the kind of visual fidelity that we're seeking. I want to show you a very simple geometric diagram to try to analyze this and get a handle on it. How dense must camera views be? So let's come up with a little toy example here where we're looking in VR, and imagine that there is some content at a near depth, z sub n, and some content at a far depth, z sub f, okay? For example, let's say we had a child in the lap example, sort of intimate graphics, intimate VR sort of situation, and front to back of the head of the child was, say, 1 foot to 2 foot away. So that'd be like 0.3 meters for z sub n and 0.6 meters for z sub f, just to give some numbers to this, okay? But let's leave that for a second and just analyze it algebraically and geometrically. So how can we reason about how dense the camera views must be? Here's one way. You could ask the question, okay, if I line in VR, so up my view so that the blue, let's say a blue dot and a green dot were perfectly occluded by each other, what's the minimum delta X lateral movement I might need to make so that I could visually distinguish the close and far features? Now, I draw it totally exaggerated here. It doesn't need to be this big. So the question is, what is the minimum delta X right here so that I could distinguish these two kind of features? Now, you can convince yourself that's going to depend on how well the eye can see. If it can see really sharply, right, then it's going to be a smaller delta X. So the theta here is intended to represent the angular visual acuity of the eye, right? Now, reminder, 20/20 vision, as we talked about last lecture in detail, the angular field acuity here is 1/60 of the degree, 1/60 degrees. It was an arc minute that came from the size of the cone cells on the fovea. So that's for 20/20 vision. But our vision in HMDs currently, head-mounted displays for VR, is less because it's not quite as high. Remember, I talked about some of the lower end HMDs are like 1/10 of a degree. Okay, they're getting better. Some are like 1 per 20. Well, what was it? Anyway, 1/10 of 1/10 degrees is sort of a low end headset today. Okay. So how can we analyze this? You can solve for theta x as a function, delta x as a function of theta, and z sub n and z sub f. I left the algebra and geometry out here, but you can take my word for it or try to derive it yourself that this is a formula for delta x, okay, given this setup here. And so you can just plug it in. For 20/20 vision, this results in delta x being like 1/1700 per foot, or for current HMDs, 1/286. What does that mean? It means that for 20/20 vision, the tiny movements from 1 foot to 2 foot away content, think of like the differentiating the fine features of hair on this child, you need millions of views per square foot. In low-end VR headsets today, you already need hundreds of thousands of views per square foot. Okay, so hundreds of thousands or millions of views compared to hundreds of views for these kinds of light field camera systems. That's sort of part of the challenge. So people have done a lot of research and said, well, what if you put a lot of cameras on a rig and then you rotate it and they're high-speed video cameras? So you can imagine in this role, right, you're capturing a lot of views. They're trying to capture hundreds or thousands of views going around by high-speed video as it's rotating. So that's one approach. Another approach that's quite current, and this is getting close to my last couple of slides here, is to use this with computational photography and modern computer vision. This is a bit hard to see. What it is, it's a plastic hemidome here. Okay, it's a plastic like half sphere. It's clear plastic, and then they sort of drill holes and they put action cameras in there. So what you're seeing here is a whole bunch of action cameras glued into this dome shape. This is Google's research on a 6 degree of freedom light field camera intended to give you a sense of virtual immersion in VR. So they took all of these camera views and then they did what I described before, like in sort of full blown. They take all of these data and they try to infer the 3D shape of the whole scene, right? The 3D depths of everything at very high resolution from all of these views using the different viewpoints and triangulation to deduce that. This is a very hard inference problem in computer vision to do accurately. And a lot of research has gone into this, and it's gotten very, huge strides have been made in just the last few years. After you do this, I'm just show you, it's hard to experience this not in VR, but what you'll see is the ability to move the parallax in the scene of the video and be able to see the kind of parallax shifts that occur. And if you develop a sort of intuitive sense for the visuals on this, this is really high quality stuff. Okay, so here's what it looks like. These are the video cameras. Action cameras are going full blown. Behind the scenes here, they're reconstructing full 3D of this scene. And then they can change both the which direction they're looking in the scene, but if you pay close attention, you're also changing to a significant degree the side-to-side parallax motion in this scene. Okay, so this is sort of state of the art. This is my last slide. So active area of research, important themes applying machine learning to intelligently upsample from the tens of camera views, right? Even that Google 6-degree freedom camera I showed you, it's like less than 100 cameras in it. So from the tens of camera views to the very high sampling rates required for that Nyquist sample VR rendering that I derived for you. One of the big problems in there is how do you infer the 3D geometry of that world really accurately? One of the really big, breakthroughs in this area has come from the research of some of my grad students that graduated last year, Pratul Srinivasan, Ben Mildenhall, and one of my current grad students, Matt Tansik, working collaboratively. And their work culminated in this paper a couple of years ago called the NERF project. So this is using machine learning-based inference of the 3D volume function of the scene from just a handful of photos. And let me leave you with the thought that this is one of the hottest areas in computer vision right now, like lots and lots of follow-on research. Matt, of course, one of our TAs, is going to give a guest lecture about this next week on Tuesday. So it's going to be a real treat. Look out for that. I really encourage you all to attend. He's going to give a guest lecture on NERFs, and he's one of the first authors on that paper. All right, folks, that's what I got for you today. That brings us to the end of VR. Good luck with the exam for those of you that are going to take it or haven't taken it yet, and have a good weekend after that. And I'll see you again here for Matt's guest lecture on Tuesday. Bye, folks.